All right, good afternoon, class. This is lesson 4. This is lesson 4 covering section 1.5 of our textbook. So with today's lecture, we are finally going to be talking about different types of solutions in practice, right? So from day one, you may recall that we briefly discussed that when we're looking at systems of linear equations, we can either have no solution, a single solution, or infinitely many solutions. And I'd stated that the case of having infinitely many solutions is going to happen when we have free variables, but we haven't really looked at examples where free variables appear yet. So I want to be able to talk more about that today so we can see some concrete examples of that. And as a refresher, what is a free variable? This is any variable. So remember when we had our matrices, a given column would correspond with a given variable. If a column is missing a pivot, then that variable associated with that column is considered a free variable. So that's what we're going to get into today. However, I want to also cover some new vocabulary with different types of systems of linear equations. So far what we've seen is that every single linear equation, or I should say, every single system of linear equations, we can write as this matrix equation AX equals B, where matrix A is our coefficient matrix, and B is a column vector, which is containing what each equation is supposed to be equal to, what each row of A is supposed to be equal to, right? So every single linear equations can be rewritten as a matrix equation. Well, we want to further break this down into two cases. Case one, we want to think about, well, what about when B is just 0? Now, when I say 0 here, really this is the 0 vector, meaning B equals a column with all zeros in the entries, right? So when I say B equals 0, I'm referring to the 0 vector, not just the single real number 0, right? Okay, but what happens when B is 0? Well, now we have the matrix equation AX equals 0. And this is where we're going to run into when we're dealing with matrices and vectors, and we're working in the world of vector spaces. What is a vector space? Don't worry about that too much. We're going to talk more about vector spaces once we get into chapter 3, chapter 4. We're going to formalize a lot of this vocabulary. What I want to highlight here, this is going to be like our first example of something weird is happening with matrix equations, which does not happen with regular algebra. What do I mean by that? Well, first of all, forget about linear algebra for a moment. Forget about matrices. If I say, okay, here's a matrix A, I have some unknown x equals 0, what x do you think would be a solution? Well, you might think if x is 0, what do I mean by 0? Again, x would have to be a 0 vector, because remember, when we do this matrix multiplication, x is a column vector. But if I make x the 0 vector, it would make sense that a matrix times a 0 vector is going to result in 0. Well, in fact, your intuition would be correct. This is a solution, right? In fact, with this kind of system, when it's equal to 0, so let me first clarify. This is called a homogeneous system, or I should say homogeneous, let me rephrase this, homogeneous linear system, because we're talking about linear equations. Right? These are homogeneous linear systems. What makes it, well, a linear system is just, as we've discussed, any matrix equation like this, right? Homogeneous is going to be the term we're going to use for any matrix equation which is set equal to 0. This is what homogeneous is going to mean here in this setting. But what we see here is that for every single homogeneous system, x equal to the 0 vector is always a solution. So x equal to 0 is always a solution to homogeneous linear systems. Why? Well, recall that the matrix A has these column vectors, let's say A1, A2, maybe there's only 2 of them. X is then containing the scalars, the entries. What am I going to multiply each column vector by, right? Recall matrix multiplication is the same thing as linear combinations of column vectors, right? And so when is this going to equal the 0 vector? Well, if x equals 0, that means x1 and x2 equals 0. And so if I take the column vector 1 or a1, no matter what this column vector is, and multiply it by 0, this column vector will now be 0. For the same reasoning, 0 times a2 will also be 0. A 0 vector plus a 0 vector is still 0, right? So x equal to the 0 vector is always a solution to homogeneous linear systems. In fact, we have a special name for this kind of solution. This is called the trivial solution. Oh, my marker is dying. This is called the trivial solution. Why do we call it trivial? Because it's always a solution. If you make x 0, yeah, a matrix times a 0 vector is going to be 0, always. It doesn't matter what this matrix A is. It doesn't matter what our equations are. If I just multiply each column by zeros, I'm going to get 0. So this is a trivial solution because it is always a solution. Now, what we're going to see is different here with matrix multiplication and vectors is we could say, well, is it possible to get a non-zero solution here? With regular real numbers, so let's back up for a moment. With regular real numbers, if I just say, let's say y times z equals 0. Well, with regular real numbers, the only way this can happen, this means either y has to equal 0 or z has to equal 0, right? However, when we're talking about matrix multiplication, right, this is different than real number multiplication. We're going to see we can get other answers. For example, consider when A is the matrix 1, 1, 1, 1, and we want to know, okay, what x is a solution to the homogeneous system? In other words, we're specifically talking about the equation. When can these column vectors combine to result in 0, right? This is what we're trying to solve. Well, we know when you're trying to solve a matrix equation, we can turn this into an augmented matrix, right? And then to solve this, I would want to row reduce it. Well, I could reduce this by just taking row 2, and I want to subtract row 1 from it. And now we get this, where something interesting has happened. We have a row of all zeros, which is fine. That doesn't mean anything bad is happening. But there's no pivot for the second column. Remember, each column is corresponding with a variable, except for the equals column, which means for x2, there is no pivot. x2 is free. What does this mean? This means x2 can be whatever we like, right? Now we know for this problem, if I make x the 0 vector, well then yes, that will be a solution, right? We know that will work. However, what other solutions could work? Do other solutions exist? Are there other things I can multiply a by where x is not 0 that I would still end up with 0? Well, according to this, x2 is free. Okay, well, x2 can be anything then. What about x1? Well, row 1 gives us the equation x1 plus x2 equals 0. Whenever you're writing down the equation for a row, you want to solve for the pivot forever and always. So we solve for the pivot. x1 is negative x2. And what does x2 equal? Well, x2 equals whatever we want it to be. It's free. We can pick x2 to be anything. So what does that mean? Our vector x takes up this form, where x1 equals negative x2, and x2 is x2. Right? This is then our solution, or in other words, this is a general solution. Right? I haven't given you a single vector, which is an answer. I've just said, whatever x2 you pick, that's going to work, right? In other words, let's just see an example. What if I pick x2 to be 1? Well, that means x1 equals negative 1. And so does this answer actually work? Well, we have negative 1 times the first column of A plus 1 times the second column of A. And lo and behold, we end up with the 0 vector. So the point here I'm getting at is that in matrix multiplication, we can have this weird thing of a non-zero matrix times a non-zero vector can result in 0. This does not happen with real numbers, but it does happen when we're talking about matrix multiplication, when we're working with matrix equations. So this is a weird thing we want to get used to. But in particular, we would also say for this system, it has infinitely many solutions. Why? Well, I just picked x2. Oops, actually marked it out. I just picked x2 to be 1. But for that matter, I could pick x2 to be 2. I could pick x2 to be 3. I could pick x2 to be 4. I can pick x2 to be whatever number I want. And so long as x1 is the opposite of that number, that will be a linear combination of these two columns, which results in 0. So for this system, we're going to see then that x equals, so we know x is this column vector where the first entry is x1, the second entry is x2. But when we row reduce the matrix, we found out x1 actually equals negative x2. And x2 gets to be whatever it wants. It can stay itself. So when we're writing our general solutions here, and in fact, what we're going to do, we're going to write this in parametric vector form. What does that mean? This is just a fancy term for how can we rewrite a given answer, right? We know our answers can be written as vectors, but what if our vectors, which can be possible solutions, can be infinitely many? Or in this case, my vector x, which is a solution, is if I factor out x2 from this vector, it's any multiple of the vector -1, 1, right? So in fact, this is the parametric vector form for the solution of this homogeneous system, right? So when we're in parametric vector form, I also want to highlight here, the only x entries which will appear in your final answer are the free variables. Your pivots will not appear in the final answer because your pivots are going to depend on what you pick your free variables to be. So this is a key point. I've had students try to write in the past, try to write their answers in parametric vector form, and they include their pivots in the answer. That is wrong. That is not parametric vector form. In parametric vector form, the pivots do not appear because the pivots, such as x1, depend on your free variables. So in parametric vector form, only your free variables are going to appear in the final answer. Of course, we're going to do more examples of this, but I want to go ahead and really showcase this example before we move on. Okay. So we had this definition for a trivial solution. That's x equals 0. This is a solution which always exists, right? We always have the trivial solution. But if you have a solution which is not 0, which is not the 0 vector, this is then a non-trivial solution. So having a non-trivial solution is something special that can happen with matrix equations, but it won't always happen. Notice here, partly why were we able to get a non-trivial solution? It was because of this free variable. Because we had the free variable, that means one of my variables could be anything I wanted. It could also be not 0 then. But if I don't have a free variable, I'm not going to be able to have this flexibility. So let's see an example of that next. And we'll get some more practice with trying to write answers in parametric vector form as well. Okay. So what about a homogeneous system where we have only the trivial solution and no non-trivial solution? Let's think about instead the matrix A equals 1, 1, 1, 2. And we want to find the solutions to AX equals 0. Find X, the X vector. Okay, well, again, we know matrix equations can be rewritten as an augmented matrix. So we have 1, 1, 1, 2. We augment with the 0 column. First column corresponds with x1, second column corresponds with x2, and we row reduce. All right, well, we're going to do the same row reduction we had before. We're going to take R2 minus R1, and we're going to have 1, 1, 0, 0, 1, 0. Now, what happened here? Now I have no free variables, and I have a pivot in every column. In particular, what does this say? Well, let's read the bottom row as an equation. This says x2 must equal 0 in order to have a solution. Okay, what does the first row say? The first row says x1 plus x2 equals 0. Well, we already know from row 2 that x2 has to be 0, which is then going to tell us that x1 also equals zeros. In other words, when we end up with this situation where there are no free variables, then we're going to find that we have only the trivial solution. X is this column vector with the entries x1, x2, but each entry, each scalar I apply to these column vectors must be 0. So this system has only the this system has only the trivial solution. And then what's the key point here? Why did this happen? There are no free variables, right? A in echelon form has no free variables. And so this system of linear equations, this homogeneous system, because it's set equal to 0, has only the trivial solution and no non-trivial solution because it has a pivot in every column for the matrix A. So this is going to be a key point forever and always for the rest of this summer class. Understanding what we have here is going to be super crucial as we continue. So make sure you understand this step, these steps here. Okay. Let's see. Let's do one more example of a homogeneous system, and then we'll look at what is called a non-homogeneous system. Okay, so what if instead I say, okay, well now our matrix A is going to equal, actually let me do it this way. There's a good example I want to talk about from the textbook. Yeah, here we go. Let's say, backing up to day 1, you're just given a system of linear equations. We're told 10x1 minus 3x2 minus 2x3 equals 0. And that's it. We're not told any other equations. We're not told any other information. This is all we're given. We're asked to find, what are the solutions? What x1, x2, x3 could work here that would be a solution for this problem? Well, first note here, we do have 3 variables, but we only have 1 equation. Okay, that's fine. We can actually still write this in the matrix equation format. How would we do that? Well, each row of a matrix is supposed to be an equation. However, in this case, I only have 1 equation, so I only have 1 row. Each column corresponds with a variable. And the last column, if I'm talking about an augmented matrix, is referring to the equals column. So I'm still talking about homogeneous systems here, where my matrix A is now this funny 1×3 matrix where we only have 1 row, right? X is then still a column vector, and it's saying, okay, what are my scalars I'm going to multiply each column by? Now, in this case, each column is only a single entry, but in our past examples, a column might have had multiple rows. In this case, it just so happens it only has 1 row. But that's fine. We can still solve this. We know in order to solve an augmented matrix, we need to put it in echelon form. That means I would like to have a pivot here. Well, lo and behold, there's no rows below it, right? So I don't have to worry about trying to get zeros below it. In fact, this 10 is already a pivot. As funny as this example is, this is already in echelon form. Can I get more pivots? No. Remember, a pivot is the leading entry of a row. If you only have one row, you can only have, at most, one pivot, right? You can only have one pivot per row. If you have a matrix with 2 rows, you could have, at most, 2 pivots, so on and so forth, right? But because of that, this is the one and only pivot. I can't get any more pivots. And in fact, I actually don't have to do anything to reduce this matrix as it is. But what happened here? X2 and X3 do not have pivots. In other words, both X2 and X3 are free. Right? So that's going to be key in trying to figure out, okay, what are answers, what are solutions to this equation? Well, what is x1? We want to solve for the pivot. 10 x1 minus 3 x2 minus 2 x3 is equal to 0. Solve for the pivot, and we end up with this equation. I'm going to add the other variables over. Oops. Divide by 10, and we get, I'm going to write them as decimals, 0.3 x2 plus 0.2 x3, and we're done. In other words, I solved for my pivot. X2 and X3 are free. So what is my general solution? Well, X is still a column vector. X1, which is a pivot, depends on what I pick X2 and X3 to be. In fact, X1 is going to be this equation. So in fact, in general, what I recommend to students when you're trying to write answers in parametric vector form, start by just writing a column vector with all of your variables. Forget about whether they're free, forget about whether they're pivots. Just start by writing your column vector with all your variables. Once you've done that, then rewrite this column vector where you set pivots equal to whatever your equation was, but your free variables are going to remain themselves. Once you've done this, now we can pull it apart into parametric vector form. Okay, what does that mean? Let's just focus on the x2s. In the first entry, I have 0.3 times x2. In the second entry, I only have one x2, so that's x2 times 1. In the third entry, I have no x2s, right? So I'm just focusing on trying to pull this apart. In fact, let me show it this way instead. Let me show you all the steps. I can think of this as 2 vectors being added together, where I have a vector with x2s in them, and I have a vector with x3s in them, right? If I add these together, it's going to turn into this vector above, right? 0.3 x2 plus 0.2 x3 will give me the exact same entry I have up here. x2 plus 0 will give me x2. 0 plus x3 is x3. Why am I doing this? Well, I'm trying to show you the in-between steps so you can see the logic behind how are we getting our final answer. I can then factor out my free variables. And now I'm going to get this for a final answer. This is then the parametric vector form for the general solution to this homogeneous system. Pick whatever favorite x2 you like. Pick whatever favorite x3 you like. Multiply these column vectors by your favorite x2, x3. Add them together, and you're going to get a new column vector, and that's going to tell you what x1, x2, x3 has to be a solution. But because we have free variables, not only do we have a non-trivial solution, we also have the trivial solution, right? If I make x2 and x3 0, which I can do because they're free, I can pick them to be whatever I want. If I make them 0, well, then this vector will be 0 plus this vector will be 0. I'll have the 0 vector. All the entries will be 0. Well, does that make sense? 10 times 0 minus 3 times 0 minus 2 times 0 equals 0. Yeah, again, the 0 vector is still a solution. The trivial solution is always a solution. You will never have a case where the trivial solution is not an answer. So what's special here is that we can also have non-trivial solutions. In particular, just to see an example of one non-trivial solution, what if I pick x2 to be 10 and x3 to be 10? Why am I picking them to be 10s? Well, I've got these decimals in these vectors, which is kind of messy to deal with. But if I make x2 and x3 both 10, then those decimals are going to go away. In fact, what is my vector x going to be? Well, I'm going to have 10 times 0.3, which is 3, plus 10 times 0.2, which is 2. 3 plus 2 is going to give me 5. What do I get for x2? Well, here I'm going to have 10 times 1 is 10 plus 0. And in fact, x3 is also 10, but that's because I've chosen them to be 10, right? Does this solution make sense? Well, 5 times 10 is 50. Minus 3 times 10 is going to be minus 30. 50 minus 30, if we're thinking about this is going to be 50 minus 30 minus 20, right? Well, of course, that equals 0. So great, we have a non-trivial solution. We have a vector, which is not the 0 vector, that when I multiply this matrix A by this column vector, it results in the 0 vector. So great, we have a non-trivial solution, but again, I have infinitely many. I could also double this. I can make this 10, 20, 20. I could make this 15, 30, 30, right? Any multiple of this vector will also be a solution. What's important isn't the magnitude of this column vector. What matters is this vector going in a direction which will be a solution for this equation? Is this going to be going in a direction which aligns with this line in this case, it would be a three-dimensional, this would be an R3 because I have 3 variables, right? Okay, good. I'm going to leave that there for a moment before we continue. So we've talked about homogeneous systems. Homogeneous systems can have non-trivial solutions, such as here. Non-trivial solutions occur when we have free variables. Homogeneous systems always have the trivial solution, but depending on whether you have free variables or not, you might also have non-trivial solutions. So that's kind of the key breakdown for homogeneous systems. And again, a homogeneous system is any matrix equation where we have AX equals 0. Okay, well, that's all fine and good. What about non-homogeneous systems? When we're talking about non-homogeneous systems, this is the second case. This is when B is not equal to 0. So we have the matrix equation AX equals B. This is a non-homogeneous linear system. Right? So what makes the difference between non-homogeneous and homogeneous? What is the matrix equation equal to? If it's equal to 0, it's a homogeneous system. If it's equal to a non-zero vector, then it is a non-homogeneous system. Now, there is a key difference I want to highlight here. The idea of trivial and non-trivial solutions, those vocabulary terms do not apply here. So again, trivial and non-trivial solutions do not apply here, right? Those are special terms which are given for types of solutions with homogeneous system. There is no such thing as a trivial solution for a non-homogeneous equation. So if you're working through this on a test or one of the homeworks, and you're like, oh yeah, here's this matrix equation, it has such and such non-trivial solution, that would be wrong, and you will lose points for that. So you want to be clear on the vocabulary here. If nothing else, linear algebra is very particular about what vocabulary is being used, right? Why is this the case? Well, for a homogeneous system, remember back in lesson 1, we said 3 cases could happen for a system of linear equations. We could have no solutions, a single solution, or infinitely many. But for a homogeneous system, we said it always had the trivial solution, which means for homogeneous systems, it is impossible to have no solution, right? So that's one key difference between non-homogeneous and homogeneous. Homogeneous systems will always have a solution. Namely, the trivial solution is always at least one solution for it. Whereas for a non-homogeneous system, it's possible you'll have no solutions at all, right? This is something that can happen, which we've seen before. If you have a pivot in the equals column, then you're going to have no solution. That would be an example of a non-homogeneous system, because that means you have something not 0 in the equals column, right? So for non-homogeneous systems, it's possible to get no solution as an answer. Okay. So let's see an example. So we're still talking about non-homogeneous systems, but I want to talk about when I'm thinking about the matrix equation AX equals B, but I want B to be not 0. We're trying to find what are solutions, what are different ways I can take linear combinations of the columns of A in order to result in B. Well, let's say A is the matrix 3, 5, -4, -3, 2, oops, -2. Yeah, let me make sure I'm copying these numbers correctly. 3, 5, -4, -3, -2, 4, 6, 1, -8. And let's say B equals 7, -1, -4. So I want to highlight some things here. One, this question we're trying to answer, there are lots of different ways of wording this question. I could say, find the general solution for this non-homogeneous system. That could be one way to word this question. I could also say, determine if B is a linear combination of the columns of A. Find the general solution. That's the same question, right? If you're trying to find out if something is a linear combination of something else, you have to put it in the equals column. You're trying to see, are there x's which would allow me to make that combination happen, right? So this is the same question. You can word it either way. It's asking the same thing. Either way, how do you solve this? Again, we need to look at the augmented matrix. 3, 5, -4, 7, -3, -2, 4, -1, 6, 1, -8, -4, and we're going to row reduce. I'd like to make this a pivot. So I'm going to take row 2, and I'm going to add row 1 to it. I'm also going to take row 3 just for space and time. I want to take row 3 and I want to subtract 2 times row 1 from it. All right, why am I doing this? I'm picking row operations which are going to create zeros below where I want the pivot to be. The first row doesn't change. The second row is going to become, I'm adding row 1. 3 plus -3 is 0. 5 plus -2 is 3. -4 plus 4 is 0. 7 plus -1 is 6. All right, what happened to row 3? 3 times -2 is a -6. That's 0. 5 times -2 is a -10. When I add, I have -9. -4 times -2 is a +8. So when I add, I get 0. And then lastly, 7 times -2 is -14. When I add, -18. Okay, so we're almost there. I'd like to get a pivot in the second column, which means I need zeros below it. So I'm going to modify row 3. And I'm going to modify it with the row that has the pivot, because I'm trying to create a pivot. So I'm going to use row 2 to modify row 3. So I'm going to take row 3, and I want to add 3 times row 2 to it. So what will that give me? Well, again, row 1 doesn't change. Row 2 doesn't change. And row 3 becomes 0. 3 times 3 is 9. When I add, I get 0. Nothing happens here because I have zeros there already. 6 times 3 is 18. When I add, I get zeros. Now, getting all zeros in a row is okay. And in fact, that's kind of a good sign. If I had gotten something that was not 0 in this last spot, I would have said, oh, I now have no solution, because if I had, say, 1 right here where the 0 is, this final row, the third row, would say 0 equals 1. So the fact that there is no pivot here in this last row and also in the equals column is good. We like this. But what we can also see is that this is now in echelon form. There's no way for me to get a pivot in the third column because the third row is all zeros. There's no leading entry left for me to use, right? This is now in echelon form. It's not reduced echelon form because I have 3's here, but this is echelon form. And in fact, echelon form is always enough to get your answer. You don't have to bend over backwards and hurt yourself trying to turn these into 1s. Leaving your matrix in echelon form oftentimes is all you need to answer the question. Okay, so what's happening here? Well, first of all, x3 is free. We can see that because there's no pivot in the third column. What's going on with x2? Well, let's look at row 2. This says 3x2 equals 6. In other words, x2 equals 2. 6 divided by 3 is 2. Now, there's a key point I want to highlight here. When I'm trying to write out the general solution from the echelon form of a matrix, notice I've been starting with the rows at the bottom and working my way up, right? The third row is all zeros. Okay, that doesn't tell me anything. Next is row 2. Row 2, I have a pivot. Okay, what does that tell me about the pivot? This tells me x2 equals 2. So now, when I look at row 1, I already have information about x2 and x3, right? Because if I think about writing row 1 as an equation, I'm going to have 3x1 plus 5x2 plus x3. Oops, hold on. I made a mistake. 3x1 plus 5x2 minus 4x3 equals 7. Now, if I had started with row 1 and I hadn't looked at row 2 yet, I would have no idea what x2 is. But because I looked at row 2 first, I'm like, aha, I already know x2 is 2. I can plug that in and make this equation nicer for me. So now I have 3x1 plus 10 minus 4x3 equals 7. I want to solve for x1. I want to solve for the pivot. So I'm going to have 3x1 equals, let's see, 7 minus 10 is -3 plus 4x3. x1 is then -1 plus 4/3 times x3. And yes, getting fractions when we're doing this kind of stuff is perfectly fine. That's a completely valid answer. So what's happened here? We solved for our pivots, and we have one free variable. So now we can write our answer in parametric vector form. X equals x1, x2, x3. Okay, what is x1? Well, x1 is this equation. And note, this equation, if you've done this correctly, when you're rewriting your pivots as an equation, only free variables will be in your answer. If you had left x2 in the equation and had put x2 in the equation here, your answer would be wrong because x1 does not depend on x2 since x2 is also a pivot, right? x1 equals -1 plus 4/3 x3. What is x2? x2 is 2. What is x3? x3 is free. It can be anything. So here's my general solution. But now in order to write it in parametric vector form, that means I need to pull it apart. So I have my free variables outside as scalars be multiplied on something. Okay, well, this also highlights it's okay to have a constant vector where there are no variables, there's no scalars being multiplied. I have a constant -1, a constant 2, and no constant in the third entry, plus 4/3 x3, 0, x3, right? I've pulled this vector apart where now I have two different vectors. I have my constants in one vector. I have all of my x3s in a different vector. All that's left now is to pull x3 out. So x equals -1 to 0 plus x3 times 4/3, 0, 1, right? This would be the final answer for this system. Now, this is a non-homogeneous system. So can I say, is this a trivial solution? Is this a non-trivial solution? No, it's neither, right? There is no trivial solution here because, well, I mean, the 0 vector doesn't even work, first of all, right? If I make x3 0, that's the only way to get this vector to be 0. I'm still left with this. The 0 vector is not even a solution here. And I wouldn't say I have non-trivial solutions because that is a term which only applies to homogeneous systems. So I cannot say I have a trivial solution. I cannot say I have a non-trivial solution. All I can say is this is the general solution for this non-homogeneous system. Okay. Now, let's go ahead and end this video with taking a look at participation. I believe it's day 4. So let's see participation day 4. we have here. So you look at participation day 4 in Canvas. This says the two below equations describe two planes in three-dimensional space. Do the two, that should say planes, not places. Little typo here. I'll fix it real quick. By the time you look at this, there won't be a typo, so no worries. Okay. The two below equations describe two planes in three-dimensional space. Do the two planes intersect? If so, describe their intersection. In other words, this is just another way of saying, is there a solution for these two equations? Is there an x1, x2, x3? Is there a vector in three-dimensional space which would satisfy both these equations at the same time? So in practice, though, you may be asking, like, okay, I can imagine this. I can imagine a plane in three-dimensional space. Why do I care, though? Like, what is this math going to help me do? In practice, it just depends on the application. You can imagine if these linear equations are representative of some kind of resource management. You're like, okay, I have point A to point B. I would like to arrive at all these different destinations at the same time. Or would you possibly need more than one truck? Would you need multiple trucks? How many trucks would you need to get the job done, right? But of course, you would want a minimum number of trucks so you don't have to spend too much money, right? You'd like to know what are the minimum number of trucks to get the job done. That is a kind of minimization problem that could be done with this kind of thing where, if this transportation of goods is modeled with linear equations, then this is exactly how you would go about solving it, right? So, okay, we want to find a solution. How do we do this? Well, you might already have guessed. We need to turn this into an augmented matrix. So I'm just going to go straight to that step. Our augmented matrix is 1, 4, -5, 0, 2, -1, 8, 9. And let me double check. I wrote this all down correctly. I would not want to make a mistake like I did last time. 1, 4, -5, 0, 2, -1, 8, 9. Good. Okay. How do we solve this? When you get into echelon form, I would like this 1 to be a pivot. I need zeros below it. All right, so I'm going to modify row 2. I'm going to take row 2 and subtract 2 times row 1 from it. Row 1 is not changing. Row 2 is then going to be 0. -2 times 4 is -8. So when I add, -9. -5 times -2 is a positive 10. So when I add, I get 18. 0 times -2 is 0, so there's no changes here. And lo and behold, what has happened? I have two pivots here, right? -9 is also a pivot. It's the leading non-zero entry for the second row. I have all zeros below it. In fact, there's nothing there, so I don't have to worry about it. But also, this is the best I can do. I only have 2 rows, so it's impossible to have more than 2 pivots, right? I can't have more than 2 pivots, which means anytime you're dealing with a system of equations where you have more variables than equations, right? In other words, more columns than rows, you will always be guaranteed to have free variables. Now, does that mean you are always going to have a solution? No. Free variables do not mean you have a solution, right? Free variables only guarantee a solution in the homogeneous system case, because for a homogeneous system, having a free variable means you have something that's not 0 that's going to work. But for a non-homogeneous system, you could, for example, and it didn't happen here, but just as a quick example, you could have something like this happen, right? This is an augmented matrix. We have a pivot here, no pivot in the second column. X2 is a free variable, right? But just because I have a free variable does not mean I have a solution. Because I have a pivot in the equals column, this system actually has no solution. Now, that's just an example. Let's finish this participation activity. The point I'm getting at here is that this is already in echelon form. I can't get more pivots, which means I can start writing out the equations. Okay, what do I have here? Well, x3 is free, so there's nothing to do with x3. What about x2? -9 x2 plus 18 x3 equals 9. I want to solve for x2. Divide by -9. 9 divided by -9 is -1. Positive 2x3. So x2 is this equation that depends on x3. What about x1? Again, this is the reason for why I wanted to find x2 first. Because now when I write out the equation for row 1, I already know what x2 is, and so I can go ahead and plug in what is x2 based on what I did with row 2. So I have x1. I'm going to go ahead and distribute the 4 here. Minus 4 plus 8x2 minus 5x3 equals 0. I want to move everything over. x1 equals 4. Let's see. Minus 8 plus 5, that's a minus 3 x3. Oops, and that should be an x3 here as well. Right? Okay, did I plug it in correctly? -4, 8x3, good. 1, 4, -5, 0, good. 4, good. Okay, so now we're ready to find our solution. X is this column vector with 3 entries. So we have x1 is this equation 4 minus 3x3. x2 is this equation -1 plus 2x3. And x3 is free. It can be itself. Again, I'm going to pull this apart. And so we can write this in parametric vector form. 4, -1, 0 plus x3 times -3, 2, 1. And there's our final answer. Now, lucky for us though, if you look at this question, all it says is to, okay, do the planes intersect? If so, describe the intersection. Okay, actually does want us to find the answer. All right, so this is then our answer. Now I realize, okay, how do you type this in Canvas, right? That might be kind of messy. Let me show you how you can type this. So let's see, let me share my screen. Share screen. And oh, has my camera been fuzzy like that the whole time? That's strange. Well, I guess I'll have to check on that later. Okay, sharing my screen. So we are looking here. So, okay, how would you type this answer in? Now I realize this might be kind of weird because these are column vectors, right? They're not rows. But because I can't exactly type in a column here, I'm just going to say x equals, and we're going to do the best we can. We know it's supposed to be -4, -1, 0. Now, yes, even though this looks like a row, we know the answer is supposed to be a column. That's okay. You can just type it in like this. I'll know what you mean. We'll both know that, hey, this is actually a column, not a row. It's just we're doing the best we can with what we can type in Canvas. Plus x 3. There might be a subscript shortcut, but you don't have to worry about that too much. You can just type x3 like this. X3 times the vector -3, 2, 1. And if you want to type your answer in just like this, that's fine. You don't have to do anything else. That will get you full credit for this question. Just hit submit, and you're golden. Okay, let me leave student view. All right, so that is all for today's lecture. Let me know if you have any questions. Keep in mind, homework 1 is due this coming Tuesday. The first office hours will be held online on Zoom. The Zoom link, I believe, is already on Canvas for that, for the office hour. Let me double check. Yeah, it's there. That will begin Tuesday night at 6 p.m. So let me know if you have questions. Email me. Otherwise, best of luck, and I will see you tomorrow. All right. Bye for now.